Ever walked into maybe a busy workshop
Yeah.
or a lab, and you instantly notice a smell?
Oh, yeah. Or sometimes you don't notice one where you really expect it.
Exactly. Like, where are the fumes? Or you wonder why some, industrial places feel pretty fresh, while others just feel stuffy.
Right. There are these unseen forces really shaping the air we breathe,
Yeah.
affecting health, safety.
Absolutely. So let's unpack this a bit. Today, we're doing a deep dive into something that's, well, foundational for safety and health. It's often working behind the scenes. Ventilation systems.
Mm-hmm.
We've got a great stack of material here for you, all about how we control what's actually in the air,
Yeah.
how these systems protect us.
And what's fascinating, I think, is how they're engineered so precisely to safeguard us.
Yeah.
It's really more than just moving air. It's managing specific contaminants, ensuring good air quality. It's this blend of physics and very practical application, crucial stuff for anywhere air quality is a concern.
Okay, so for you listening, our mission today is kind of demystify this invisible shield. We're going to break down the two main ways of thinking about ventilation.
The core strategies.
Yeah, the strategies. And the principles that make air move, how the systems are designed, the components, all of it. Get ready to understand this, like
Okay.
engineering shield, protecting our lungs.
Keeping workspaces safe.
Exactly. So when we talk about keeping air clean, it sounds like it's not just one method fits all, is it?
No, definitely not. Our sources point to two really distinct approaches right away.
Okay.
Think of them as two very different strategies, really. First, you've got general ventilation, sometimes called dilution ventilation.
Dilution. Okay.
This is probably the one most people sort of intuitively get. It's like opening a window, airing out a room.
Right. Burnt toast smell.
Exactly that. You're bringing in lots of clean outside air to mix with the contaminated air inside. The goal is just to lower the concentration of whatever contaminant is there.
Dilute it down.
Dilute it down below some acceptable level, like a threshold limit value, a TLV for health, or maybe a lower flammable limit, LFL, if you're worried about fires or explosions.
Okay, so if you're dealing with something maybe not super toxic, generated kind of slowly, spread out, this sounds pretty good, right? Simple.
It's definitely best for those scenarios. Low toxicity, low generation rate, sources spread out, works well.
But there have to be limitations.
Oh, absolutely. And this is important. What are its limits? Well, first, it doesn't actually get rid of the hazard.
It just waters it down.
Yeah, it dilutes it, spreads it out. So right at the source, where the contaminant is being made, concentrations can still be really high. Bad news for anyone working right there.
Ah, okay.
And the other big thing, cost.
Yeah.
Especially energy costs. If you're constantly pulling in huge amounts of outside air.
You got to heat it or cool it.
Exactly. That makeup air needs conditioning. And that can get incredibly expensive, especially in, very hot or very cold climates.
Yeah, I could see that hitting the budget hard. Okay, so dilution works sometimes, but not always. What's the alternative then? When things are more serious, more concentrated, or toxic?
Well, that's where the sources pivot to a totally different approach. Almost the opposite, really. Local exhaust ventilation, LEV.
LEV.
And LEV is generally the preferred method for most airborne hazards. Why? Because it tackles the problem at the source.
Before it spreads.
Precisely. Instead of diluting it throughout the room, LEV systems are designed to capture contaminants right where they're generated before they escape into the general workspace air. It's much more targeted.
Surgical, like you said.
Kinda, yeah. And it's a system, right? Not just one thing. Usually you have a hood. That's the capture point. Then ducts to transport the contaminated air away.
Okay.
Then an air cleaner or a collector that removes the contaminant. And finally, a fan. The powerhouse that moves the air through it all.
Makes sense.
And the advantages are pretty clear. It's highly effective, especially for toxic stuff. It needs way less total air volume compared to dilution.
Which means less heating and cooling cost.
Big savings there, yeah. And crucially, it stops the contaminant spreading, protects everyone in the area, not just diluting the risk.
Got it. So one's like a wide spray setting, the other's a fine jet, hitting the problem right where it starts.
That's a great way to put it.
Okay, so we understand what the different strategies.
Yeah.
How about the how? Let's get into the nitty-gritty, the physics behind it all. How does the air actually move?
Right.
Our sources dive into some core principles, some key equations. Where's the starting point for understanding that?
Well, fundamentally, it all comes down to airflow, usually called Q. That's just the volume of air moving through a duct over time. Think cubic feet per minute, CFM.
Okay, how much air?
Yeah. And it's pretty intuitive, actually. Airflow Q is just The velocity, V of the air, multiplied by the cross-sectional area A of the duct.
So Q equals VA. Speed times the size of the pipe.
Exactly. That tells you how much air is actually being moved. It's the first thing you check if a system isn't working right.
And what actually makes it move? It's got to be pressure, right?
It's all about pressure.
Right.
Absolutely. And there are 3 types we need to understand in a duct system.
3.
First, static pressure, SP. Think of this as the potential energy. It's the pressure pushing outwards on the duct walls or pulling inwards if it's negative pressure, measured perpendicular to the flow.
Like air in a balloon.
Kinda, yeah. That's the kinetic energy. The pressure purely from the air being in motion, always positive, always acts in the direction the air is moving.
The force of the air moving.
Right. And finally, total pressure, TP, is just the sum of the two. TP equals SP plus VP. Simple addition.
Okay, so static is the push, velocity is the whoosh, and total is both together.
Yeah, that's a good way to think about it, the push and the whoosh.
And
And understanding this is key because, well, engineers use it. There's a direct link between how fast the air is moving, its velocity, and that velocity pressure.
so you can measure one to find the other.
Precisely. There's a specific formula our sources give. V equals 4,005 times the square root of VP. So V equals 4,005 rad P.
Okay.
This lets engineers calculate the air velocity in feet per minute just by measuring the velocity pressure, usually in inches of water gauge. Or they can go the other way. Super useful for designing systems, balancing them, figuring out what's wrong.
Right, and you mentioned dilution ventilation earlier. Our sources also had some equations for that, didn't they, for calculating concentrations?
They did, yes. Very important tools for dilution design. For steady-state concentration, there's an equation to figure out the ventilation rate, VR, you need to keep a contaminant, say a solvent vapor, below its limit.
Okay.
It uses things like the liquid-specific gravity, how fast it evaporates, its molecular weight, and really importantly, a safety factor.
The safety factor.
Yeah, usually a number between 3 and 10. It's basically a buffer. It accounts for the fact that mixing in the real world isn't perfect, air might not move evenly everywhere.
So it builds in some extra protection.
Exactly. A higher K means more safety margin. Maybe 3 for a simple setup, maybe 10 for something complex or really critical. And then there's another equation for concentration buildup. That one lets you predict how the concentration changes over time.
Like how quickly things get bad if the ventilation stops.
Or how long it takes to clear out once it starts. It looks at the generation rate, the ventilation rate, and the room volume. These let engineers design proactively, not just reactively.
Makes sense. Predictive power.
Uh,
Okay, let's circle back to LEV, local exhaust ventilation, because you said that's often the preferred method.
it usually is, yeah. Especially for more hazardous stuff.
So how do we make sure that system, that targeted system, is actually grabbing the contaminant like it's supposed to?
Well, the absolute key is the hood,
Hmm.
and specifically achieving the right capture velocity.
Capture velocity. Okay, what's that?
That's the speed of the air at the point where the contaminant is being released. It has to be fast enough to overcome any room air currents, drafts, people moving.
And suck the contaminant into the hood.
Precisely. Pull it right in before it gets away. And this velocity isn't one size fits all.
No.
No, our sources show a huge range. For something slow-moving, like fumes gently rising from a tank, maybe only 50 feet per minute, FPM, is needed.
Okay.
But for something really energetic, like, say, grinding metal or abrasive blasting,
Lots of dust flying around.
yeah, dust with momentum, you might need 2,000 FPM or even more. And the source to capture that effectively, it really depends on the process.
Wow. Big difference. So the hood itself, its design must be pretty important too. Not just any funnel shape will do.
Oh, absolutely. Design is critical. And one simple but really effective design feature is adding a flange around the hood opening.
A flange, like a lip.
Exactly, a lip or rim around the edge. It sounds simple, but it makes a big difference. It basically stops the hood from pulling in air from behind it.
So it focuses the suction forward.
Exactly. It makes the capture much more efficient for the same amount of airflow. You get more bang for your buck in terms of capture velocity.
Less wasted effort pulling air from places it doesn't need to.
Right. There's even an equation for flanged hoods. Q equals 0.75 V, 10x plus A, where x is the distance from the hood face to the source. It shows mathematically how much better a flange is.
So less airflow needed overall.
Potentially, yes. Or better capture for the same airflow, which means maybe a smaller fan, lower energy use. It all adds up. Smart design pays off.
Okay, so the hood grabs it, then it goes into the ducts. What's the key consideration there, just getting it from A to B?
Well, Yes, but you need to make sure it stays moving. We need adequate duct velocity or transport velocity.
That's your velocity.
This is the speed of the air inside the duct. And it has to be fast enough to keep whatever you've captured suspended in the air, especially important for particles like dust.
So they don't just settle out.
Exactly. If the velocity is too low, dust will drop out, settle in the bottom of the duct, build up.
Clog the system.
Yeah, clog it up, reduces performance, creates potential hazards, needs cleaning. It's bad news. So you need enough speed to keep everything air-borne until it reaches the air cleaner.
And that speed also varies, I assume.
Hugely. Again, depends what you're moving. Simple vapors might only need around 1,000 FPM, but heavy dusts, or maybe sticky or moist dusts, you might need over 4,500 FPM.
Wow. That's moving.
It really is. You need enough speed, but not too much, because higher speeds mean more energy use and potentially more wear and tear on the ducts from abrasion. It's a balance.
Okay, capture velocity at the hood, transport velocity in the ducts. What's providing the actual power for all this, the engine of the system?
That's the fan. The fan is definitely the heart of the system. It provides the energy, the pressure to move the air through all the components, hood, ducts, filters, everything that resists airflow.
Right. And there are different types of fans, too.
Yes, our sources mention two main types. First are axial flow fans. Think of a propeller in a tube.
Like a desk fan, but bigger.
Basically, yeah. They move large volumes of air, but they don't generate very high pressure. They're good for general ventilation, just moving air around a room where there isn't much resistance.
Okay. But for these LEV systems, with all the ductwork and filters, that sounds like a lot of resistance.
It usually is. And that's where the second type comes in. Centrifugal fans.
Centrifugal.
These look more like a paddle wheel or a hamster wheel inside a housing. They spin the air outwards using centrifugal force.
Okay.
And these are much more common in exhaust systems, especially LEV. Why? Because they can handle air with particles in it better, and crucially, they can generate much higher static pressures.
To overcome all that resistance you mentioned.
Exactly. They can push or pull air against significant pressure drops from long ducts, filters, bends, and so on. They're the workhorses for LEV.
And it's not just picking the right fan type. There are these fan laws mentioned in the sources. They sound kind of important. They describe how fans behave if you change things.
They are incredibly important. The fan laws are fundamental. They predict what happens if you change, for instance, the fan speed, its RPM.
Okay, so what does happen? Let's say you double the fan speed.
Right, good example. If you double the fan speed, RPM, according to the fan laws, first, the airflow Q also doubles. It's directly proportional.
Makes sense. Faster fan, more air.
Second, the static pressure, SP, the fan, can generate quadruples. It goes up with the square of the speed change.
Wow. Okay. Double the speed, 4 times the pressure capability.
But here's the kicker. The brake horsepower, BHP, the power needed from the motor to turn the fan increases by a factor of 8.
8 times.
8 times. Power is proportional to the cube of the fan speed change.
That is a massive jump, just from doubling the speed.
It's huge, and it shows why you can't just casually speed up a fan to get more airflow. A small increase in desired flow can lead to a massive increase in power needed.
You could overload the motor or just run up an enormous energy bill?
Exactly. It highlights the need for careful design and selection. Making seemingly small tweaks can have really significant consequences for energy use, cost, and even whether the motor can handle it. Precision matters.
Absolutely. Okay, so fan provides the power, moves the air through the ducts. But we captured contaminants. We can't just dump that air outside, can we?
No, definitely not in most cases. That's where the air cleaning devices come in. Absolutely essential.
The final stage.
Right. They remove the contaminants from the airstream before the air gets discharged outside. Or sometimes, if the air is cleaned really well, it might be recirculated back into the workspace to save energy, but that requires very careful design and monitoring.
Okay. And there are different ways to clean the air, too.
Oh, yeah. A whole range of technologies depending on what you need to remove. For larger particles, you might use mechanical separators like cyclones. They spin the air and the heavier particles get thrown out.
Okay.
Then there's filtration, very common. Think fabric filters or bag houses for collecting dust. For really, really fine particles, you use HEPA filters, high-efficiency particulate air filters.
Like in clean rooms.
Exactly, or for hazardous dusts. Then for wet stuff or even some gases and vapors, you can use wet collectors or scrubbers. They use a liquid, usually water, to trap particles or absorb gases.
Scrubbing the air clean.
Literally. There are also electrostatic precipitators that use electrical charges to make particles stick to collection plates. And for specific gases and vapors, gas adsorbers are used. Things like activated carbon.
Like in a water filter, but for air.
Similar principle, yeah.
Right.
The gas molecules stick to the surface of the carbon, so lots of tools in the toolbox.
A whole arsenal, really.
Yeah.
Each designed for a specific type of problem. It's not just one filter does everything.
No, absolutely not. Often you need multiple stages, maybe a cyclone to get the big stuff, then a baghouse for the medium stuff, maybe even a HEPA filter at the end if needed. Choosing the right cleaner or combination of cleaners is critical for the system to work effectively and, legally.
Right, to meet regulations. Okay. So putting it all together,
Mm.
what's the big takeaway here? We've gone through dilution, local exhaust, pressure flow, fans, filters.
Yeah, we've covered a lot of ground.
We really have. It seems like we've journeyed through this like invisible world of ventilation, understanding how these systems work behind the scenes.
And I think if we step back, the big picture is that proper ventilation isn't just about comfort or blowing air around.
No.
It's a critical safety control. It's engineered. It's a silent guardian, protecting us from hazards we often can't see, can't smell.
Yeah.
And it really demands, precise engineering, understanding the physics, getting the components right.
It's complex. Whether it's keeping scientists safe in a lab or dust out of a workshop or fumes clear in a factory.
Or even just keeping a concert hall feeling fresh.
Right. These systems are doing that heavy lifting invisibly. This deep dive, it's really shown that what we don't see is often what's most vital for our safety.
Well said.
So here's something to think about. The next time you feel a draft indoors, maybe near a vent, or you hear that hum of an exhaust fan, just pause for a second. Consider that complex dance of physics and engineering happening just out of sight, protecting you. What might be going on in your own workplace or even your home that you've never really thought about, all thanks to these systems?